Good morning, good afternoon, good evening. Whenever you are watching this video, let me welcome you all to our channel Future Endeavors. Okay, so we are posting this video after a long time. There were some health issues due to which we cannot upload any videos during this time. It's a tough situation for all of us. I hope you are all okay and in good health. So, without wasting much time, I will be giving one more lecture on current electricity. So this will be the concluding lecture. We have so far discussed about current, potential difference, and resistance and Ohm's law. Along with that, we have also discussed about the combination of resistance and done some few numerical problems. Although those few numerical problems are not enough, however, if time permits us, we will definitely solve some more problems. Okay. So today we will be discussing about electrical energy and power. The last part of this chapter, electrical energy and power. Electrical energy and power. So first of all, let us talk about electrical energy. So how can you define or how can you relate electrical energy with the known quantities, that is the voltage, current, resistance that we have till now discussed. So I think all of you have remembered the definition of potential or potential difference. See, we have said that potential difference is nothing but the work done per unit charge. Okay, so from the definition of potential difference you can write that W equals to V by Q naught, where Q naught is the test charge that you have taken under consideration. V is the potential difference between the 2 points, and W is the amount of work done in moving the charge Q naught between those 2 points. Okay. So with this knowledge, you can say that have I written it correct? I don't think so. There is a slight mistake. So this would be V equals to W by Q naught, isn't it? Okay. So please rectify the mistake. Okay. So V is equals to W by Q naught. Potential equals to work done by charge. Okay. So from this definition, can you, or from this mathematical relation, can you say that then W is equal to V into Q, or say rather Q naught. Okay. So I think you know that work done and energy can be treated as similar things, isn't it? By now you have known that what is energy? Capacity for doing work. So whatever mathematical formula is there for work, you can actually use it for calculation of or any kind of energy. So from that definition, from that concept, we can say that the work done in moving some charge from one point to another point is given by the product of the potential difference between the 2 points and the amount of charge that you are moving. So what is this? What is this W? Can I say that this W is actually the electrical energy between the done or accumulated in a system when some work is done to move the charge, isn't it? This is the electrical energy, isn't it? So I can say that electrical energy E can be taken as V into Q. From the definition of current, you know, we have defined current already. So from the definition of current, you can say that current I is equal to Q by T, isn't it? So what will be the charge Q? It will be I into T, isn't it? Okay, I into T. Fine. So from that we can substitute the value of the Q into the equation for the energy, isn't it? So if I just substitute this value here, what I get? I get V into I into T. So this is the expression for electrical energy, which relates electrical energy with the known parameters that you can actually get: current, voltage and time. You know, you can very easily find out the current in a circuit using a device called ammeter. You know this, and you can easily measure the potential difference of the voltage across a circuit using voltmeter. So it is easier for us to measure the current and the voltage. So if you know this current and voltage, you can easily calculate the amount of electrical energy being consumed in that circuit for a certain time t. Now there are two other forms also. This is one form. Now you know Ohm's law, isn't it? You know Ohm's law. What does Ohm's law states? Ohm's law states that V is equal to IR. I am just talking about the mathematical expression. So if I just put this value of V here, what will I get? If I put the value of V here, I will get E is equals to, instead of V I write I into R into I into T. This turns out to be I square R into T. So this is the second expression by which you can calculate the electrical energy if you know the current and the resistance. Okay, and again, if I from this very Ohm's law, if I substitute that current is equal to I is equals to V by R, isn't it? If I substitute this value of current here, instead of substituting the value of the voltage, if I substitute the value of current in this equation, what will I get? So let us see. E is equals to I. What is I? So V into I means V by R into T. So this turns out to be V square by R into T. Okay. So this is the third formula which relates the electrical energy with potential difference and resistance and time. Okay, so what are the three formulas that you are getting? E is equals to, either you can calculate it using the formula VIT, or another formula is I square RT, or another formula is V square by R into T. So these are the three formulas which you can utilize to calculate electrical energy, isn't it? Okay. If you have any doubt regarding this, please pause the video and once again go through the video. It will be easier for you to understand the concepts. Okay. So I think electrical energy is, by now it is clear to all of you. Okay, good. Now, what is power? You know, so this is the electrical energy that you are getting. Now, what is the power? So, what is power? Okay, just to remind you, what is the unit of energy? Unit of energy is Joule. So, obviously, when you are calculating electrical energy, you can calculate the electrical energy in terms of Joule. So, unit of electrical energy is Joule. Okay, fine. Now, let us come to power. So, what is electrical power? Now, you know that power is nothing but the rate of doing work, or rather you can say work divided by the time. Simply you can also put it as energy divided by time. So, power is energy by time, isn't it? Energy by time. Now you have already obtained the expressions for the electrical energy. Just simply put the value of these three equations in this equation. You will get the expression for the power. So P is equals to, first equation that I will be getting. So first equation was V into I into T divided by the time T. You will get the electrical power as V into I. Okay, so this is a very first equation. Power is the product of the voltage, that is the potential difference, and current. Okay, fine. Now, second equation. So power equals to, what is the second equation of the energy? It was I square into R into T divided by time T gives you I square R. So this is the second equation. Fine. And what is the third equation? P is equals to V square by R into T. This was the equation. So divided this equation by time T. Again time T cuts off. By simplifying, you get V square by R. So these are the three equations that we can use to calculate power in an electrical circuit. Okay. So I think the concept is very much clear. And if you talk about the unit, SI unit of electrical power, we say it as watt. Okay. So unit power is what is what? What is Joule? It is Joule by second, isn't it? So that gives us what? Joule by second. So this is the concept of electrical power. So to sum it up, just let us see, to sum it up, how we have, so what are the formulas that actually we have. So just easing it off. If you have doubt about this portion, just pause the video, rewind it and go through it once again. I think it will be absolutely clear to you. Okay, so summing up, what are the formulas for the energy? Just let us see. Energy, we have three formulas. First one was V into I into T. Corresponding, what are the formulas for the power? So power is V into I. Second formula turns out to be I square into R into T. This turns out to be I square into R. Third formula was okay, I square R. Third formula was V square by R into T. So here it will be V square by R. Okay, so these are the three formulas. Now remember one thing, the first formula can be utilized anywhere. Generally this second formula is applied when you have a series connection of resistors. Series connection. So the second formula is generally used for series connection. Okay, so this is used for series connection. Remember it will be easier for you to calculate or to do the problems. And because in series connection the current remains constant, so we are using these two particular formulas for calculating the energy and power while the connection is given in series. And when the connection is given as parallel, the combination of parallel resistors, so we use the last formula or third formula for the calculation of the power and energy and power, parallel connection. Okay, so the third equation is for parallel connection. Okay, so it will be easier for you to calculate the values if you follow this convention. Fine. Okay, so the concepts I think are clear to you by now, to all of you by now. So this is the electrical energy power. Okay, now let me discuss another thing. See, we have seen that the SI unit, normal SI unit for electrical energy is Joule. Obviously, electrical energy is a form of energy, so definitely energy has a SI unit of Joule. So definitely electrical energy will also have the SI unit of Joule. But actually, we do not use Joule as the preferable unit for calculating the electrical energy. So what else in a unit can be used for measuring the electrical energy, specifically for electrical energy? Now let us see. See, there is a special unit that we use for calculating the electrical, for expressing electrical energy. See, you know that power is equals to energy by time. So definitely energy will be equal to power into time, isn't it? Power into time. Now if you consider that we are taking the unit of power as kilowatt. Okay, kilowatt is a unit of power, as you know. And if I consider the unit of time to be hour, not second, we are just taking it as hour. So this kilowatt multiplied by hour is a unit for electrical energy. Kilowatt hour. In short we write kWh. Okay, kilowatt hour. So this is the most common unit that is being used to measure the electrical energy, and in most of the commercial cases we use this particular unit, kilowatt hour. Okay, kilowatt hour. Now often this unit kilowatt hour is referred to as the commercial unit of electrical energy. Commercial unit of electrical energy. Okay, why commercial unit? You know, or it is also sometimes written as board of trade units. Board of trade units. Okay, BOTU, board of trade units. Okay. Now, you may have seen electrical bills being delivered to your home within a certain definite span of time. Now, there it is written at the top of the electrical bill that certain units of electrical energy has been consumed within a say month of 1 month or month of span of 3 months. Okay, that say it has been written that you have consumed, if you see the bill, you will see that you have consumed certain amount of electrical units of electrical energy. Nothing is written there, but it is only written, say you have consumed 300 units of electrical energy. So what is the unit? That unit that is being referred there is nothing but kilowatt hour. Okay, nothing but kilowatt hour. So how can you define kilowatt hour? So what is this kilowatt hour? Can you say what is this kilowatt hour? So what is this kilowatt hour? Now see, generally the appliances are rated by their power ratings, and if you see the appliances, the voltage rating and the power rating are marked on the appliances. Now if I say a device which has been marked as 1 kilowatt, 1 kilowatt means 1000 watt. If a device has been marked as 1 kilowatt and that device runs on for say 1 hour, then the energy that it will be consuming is regarded as 1 kilowatt hour, and that is referred and can be referred that you have consumed 1 unit of electrical energy. So whenever you run a device which is rated as 1 kilowatt for 1 hour, you will be definitely sure that you have consumed 1 unit of electrical energy, and the electrical companies that supply electrical energy to our houses charges us accordingly. They, at some places it has been charged as say 5 rupees per unit. Per unit means per kilowatt hour. So if you just run an appliance of say 1 kilowatt for a time span of 1 hour, you have consumed an electrical energy equivalent to say that rupees 5. Okay, so that's for an example. So kilowatt hour is nothing but it is the amount of energy consumed by a device of 1 kilowatt when it is operated for 1 hour. So I think the definition of 1 kilowatt hour is clear to all of you. Okay, so this is 1 kilowatt hour. Now what is the relation of 1 kilowatt hour with joule? Can you guess what is the relation between the 1 kilowatt hour and joule? Very simple. Say 1 kilowatt hour and joule. How can we relate this? Okay. Say 1 kilowatt hour. So I am considering 1. Okay, so 1 kilowatt means 1000 watt, and 1 hour means 3600 second, and watt is joule per second. So watt into second is joule. So this turns out to be 3600 into 1000 watt second. So this watt second is nothing but joule. So 36 into 10 to the power 5 joule, or it can be regarded as 3.6 into 10 to the power 6 joule. So I think the relation between kilowatt hour and joule is clear to all of you. Another unit that we use generally for electrical energy is 1 electron volt, 1 EV. It is equivalent to 1.6 into 10 to the power minus 19 joule. Generally we use this unit electron volt EV when we have very small electrical energies. So for small electrical energies we often use this unit electron volt. So I think the lecture is clear to all of you. So we are ending this chapter here. Next we will be starting with household circuits. So till then we will be very soon uploading the next video. So till then please stay tuned, stay safe and stay healthy. Okay, so thank you, goodbye.